All right, welcome you guys to Experimental Designs. This is where we start getting into the nitty-gritty of exactly how we're going to conduct the tests with our sample of the population. Now that we have um, ethically considered everything we need to consider, we've gone through all the work of choosing measurements, all those other things. Now we can finally get to the testing of our research question. And so this first week, we're going to be dealing with two-group design. It's the most basic causational experimental design. We're going to get some of the basics out of the way and talk about what it looks like and some other really important things to know about experimental design as a whole. So before we get into some of the more nuanced pieces of experimental design two group, we're going to start with some remembering the basics we need to know before we get into experimental design. So remember that there's a difference between experimental and non-experimental. Non-experimental is that exploratory topic where we're not really sure what kind of relationships might be out there between variables. We're just measuring stuff to see what might be out there. Non-experimental designs, they describe if there is a relationship between variables, but nothing about how those variables interact and in which direction they interact, if one causes two or if two causes one, things like that. Non-experimental designs just aren't statistically set up to determine causality, and it's much more about observing variables in their hopefully in their natural habitat, but sometimes in a controlled environment as well, but much less about manipulating them. Over in the experimental side, we have to get very specific with our research topics. We have to get specific with our research definitions and our terms that we use. We have to get specific with the measurements we use. We seek the strength of causational relationships, so not just that there is a causational relationship, but how strong is that causational relationship between 1 and 2, A and B. Sometimes an experimental design can determine causality, but it's less about determining and much more about supporting. A hypothesis is supported or unsupported at the end of an experimental design. Even after a really strong experimental design, you can't walk away and say, haha, I proved it. You need much more than a single experiment to make a claim about a phenomenon. And lastly, about experimental designs, the independent variable is actually manipulated. It's changed up and down to see what happens to the dependent variable. It's not just being measured, we're actually manipulating a variable. Some things that are really important for experimental designs and non-experimental designs are how are you keeping the validity strong and how are you choosing your measurements, right? So validity is about how consistent your research design is internally and externally, how it can be generalized outwardly, and how well it holds up in its own scrutiny internally. So some things to know about validity. We need to start with really strong definitions about the terms we're using. Make sure that everyone agrees on these terms, that we're not just creating new terms out of thin air without having a really good reason to do so. We also try to make sure that all the extraneous variables that could mess with my experiment have been controlled for. That way I know that what I'm studying, what I'm manipulating in my independent variable is the thing causing change in the dependent variable. We try to make sure that all of my own biases have been reduced through anonymity, through blinds, which we're going to talk more about in a bit. And we're also making sure that every possible ethical quandary has been considered. We don't want to start any research without first considering who might be harmed and who might be benefited. And just a quick recap on measurements. Do your measurements make sense to use? Are they consistent and reliable? There's tests for that. Have they been used by other people? So that way we know we're all talking about the same thing, measuring the same thing. Are your measurements strong enough and varied enough for big, complicated terms? You can't just say public health and then have one measurement for it. There's lots of aspects to that. So are we making sure that do we have enough measurements to capture all of that topic, all of that term? And then we want to make sure that measurements, even though they're doing a good job staying consistent, are we being consistent in how we apply them? Now let's get into some new terms. Now that we're dealing with an experimental design, we have some more variables to consider. One being a mediator variable and one being a moderator variable. These are different than confounding variables, and they're different than independent and dependent variables, and we'll talk more about them here real quick. So let's start with mediator variable, right? So on your screen you can see the definition. I'm going to read that real quick. The specific connection between an independent variable and the dependent variable that kind of explains how the two directly connect, right? So it's easy to have an independent variable, and it's easy to have a dependent variable, and it's kind of easy sometimes to show that the independent variable does affect the dependent. But the next question is, well, how is it that they're touching? How is it that these two variables are actually working with each other? So we can see here, I've got an example. A new workout regimen for a team, a new workout plan for a team can improve team performance, right? So the independent variable here is that new workout schedule, that new workout regimen. And then team performance, either in games or in longevity or like better scoring, depending on the game itself. That's the dependent variable. And we might be able to see pretty quickly that the workout regimen, as we increase or decrease the workout regimen, the new one, team performance can go up or down also. But the question is, what about that new workout regimen is actually changing the team, connecting to the team performance? So the mediator variable here, for example, is what kind of rest is included in the new workout regimen, right? What time is rest taken? How often? Are we talking micro 30-second rests during the workouts? Are we talking 5 to 10-minute rests in the workout? How do those rests immediately impact performance? Or that would be the mediator. But through the regimen, we have rest that interacts more directly, more concretely with team performance. So that's mediator variable. The next variable that we're going to talk about is moderator variable, and you can see the definition there. This is a third variable outside of what we're controlling for that influences the directionality and strength of the relationship, right? So which way is the relationship going is here. So my example, I've got food incentives can improve class attendance, right? If someone brings brownies every day, if a teacher brings brownies to class every single day, that might impact how much attendance routinely happens. But one thing is food allergies might say if someone shows up more or less, right? That's directionality of the relationship. Food incentives might generally say people might increase their attendance, but for a few people who have allergies, it might decrease their attendance. But what if we change the brownies, the food incentive, to gluten-free? Suddenly, those allergies being accounted for changes the directionality of that relationship. So mediator variables and moderator variables, they're technically not something we account for directly, but you can try your best, or even try your best to address it in your written article. But they're typically things that kind of dictate a stronger, more nuanced relationship between the independent and the dependent variable. So now that we've set some of the groundwork, let's talk more about what exactly a two-group design is. Don't worry, it's very simple. So a two-group design is exactly what it sounds like. So say we've already gotten a sample from our population that we want to study. We've already gotten our group of people who are participating in the research as part of the research. There we have our sample, right? And in my little picture here, they're all very happy. And then we go through dividing them into two different groups, right? One group will get the independent variable or the treatment, and one group will not, and one group will not. We call this the control group and this the treatment group, right? So with the treatment group gets the independent variable, gets the manipulation of the variable, and their scores, their measurements, will be compared against the control group, right? The control group will typically go through something similar but not the same as the treatment group, just so that we know that all variables have been accounted for. All variables have been accounted for. So you can see through here, through the arrows, that after we have divided people either into control or treatment group, that they're going to go through a pre-test, then treatment or no treatment, then a control post-test. Now, there are some two-group designs that have no pre-test. It's just treatment, pre, and then post-test to get those answers. But we typically like a pre and a post test for all group designs if possible, because then you can account for any changes within the control group that just naturally happen, right? That pre-test and that post-test can work together in the control to tell us if people just change because they change from being here or not. And that will help us understand much more if the independent variable from the treatment group actually does have an effect or not. The treatment group, they will go through a pre-test, treatment, and then post-test as well. And we're going to see if those numbers change from the pre-test to the post-test, but then we're also going to compare them to the pre and the post-test of the control group. So another way to think about this is after we have divided the groups into two, we want to make sure that simply taking the test doesn't change answers all on its own, right? And that's why we have a control group. They may not take the test the same way. They may not interact with the independent variable in different levels, but they are going to go through some form of testing that or measurement so that that variable simply taking the test is not unaccounted for or is not messing with the whole design, right? That way we can look at test taker bias and hopefully account for test taker bias by simply making sure that everyone takes the test. So another thing to know here is you'll see that random or blind assignment is how we assign people to one of the two groups. That's important because of researcher bias, right? I don't want to just put people in the control group because I do or don't like them, or because I have some sort of bias I can't really name very well. I want to flip a coin and assign people randomly. I want to assign people randomly. There is another way to do random assignment called matched pair. This is where we take participants who are very similar in key characteristics or key traits, and we very intentionally take these two and split them up. We don't want them both to take the control and both to take the treatment. We want to see, because they're so similar, if we split them up, if the control group and the treatment group are making a big difference. The fact that they are so similar is exactly why we want to split them up. It gives us a bit more information on the experiment, on the independent variable as a whole. The thing is, after we split them up, we can't just say, well, I get to then choose which of these people goes into which group. We still need to make sure it's random to some degree. So even if we're splitting them, we've got to flip a coin for the first one, and then the second one will go in the opposite group. So matched pair is very helpful in making sure that key characteristics and key traits are accounted for as an extraneous variable, but we can't just pick our favorite of the two, right? We have to keep it random to some degree to avoid researcher bias. So to make sure we reduce interference with the research design, we want to make sure that researcher bias is controlled for and that the control group is also taken care of and protected from any extraneous variables. So for the researcher side of things, we have blinding methods. Not blinding like losing sight, but blinding in the sense of reducing or creating separation between the researcher and the experiment. The more distance we can create, the more likely it is that researcher bias did not play a part in whatever effects we see at the end, right? So blinding is a method of creating anonymity between researcher, analyst, and participant scores. 1, 2, 3, researcher, analyst, participant scores. So a single blind is the participants don't know if they're getting the treatment or not, if they're in the independent variable group or not, if they're in the experiment group or not. That's single blind. And that's one of the reasons we make sure that there's a pre and a post test for both the control and the treatment group, because it kind of creates a bit more confusion about which group am I in. Well, you don't know, so we get more honest answers that way. That will be the single blind. The double blind is going through a process where even the researcher might not know which group each participant is in, right? With things like drug studies, this is a lot more simple. The researcher doesn't know if they're giving a participant a placebo pill, a sugar pill, or the treatment, right? The researcher just knows that, hey, I'm giving everyone pills, right? And then some other researcher set up which pill is which, but I won't know. It's just that researcher back there who does know. So if single blind is about the participants only, and double blind is about participants and the researchers, triple blind is where participants, researchers, and analysts have no idea who belongs to what group until the very end. So a triple blind is where the people who are taking the test don't know what group they're in. The people who are administering the test, giving the test, they don't know what group people are in. And the people who are conducting data analysis, statistical analysis at the end, they don't know which group people were assigned to. That's when we typically use things like temporary IDs. It's where the person who's administering the test was like, here's an ID code randomly generated for you, but I don't know what it is. Don't show me, right? And that ID code kind of hides their identity, even from the statistician who's doing the research. And that triple blind kind of creates the most distance between researcher and participant scores, which is one of the strongest ways to reduce researcher bias. Now, it's not always possible to do a single, double, or triple blind, but wherever you can, it is highly recommended that you do so. And then we move over to taking care of our control group, making sure our control group doesn't have any extra layers put on top of them. And there's a couple of different ways to do that, right? An easy one is a placebo. An easy one is a placebo where you give false or intentionally ineffective treatment. That can look like a sugar pill. That can look like a sugar pill. Or sometimes, if it's like a talk therapy treatment, you just tell them something about a baseball game. And that when talking about a baseball game, we know is not super helpful in dealing with XYZ, dealing with the dependent variable. So we know that that would be like a placebo kind of talk treatment. There's another kind of control group where we have this wait list approach. This is where people are measured and then given treatment later than other participants, right? So one group of participants might be given the treatment, and then the second group, we just wait and don't give them the treatment yet. And we get their scores in, and then we give them the treatment later. So you're on the wait list to get the treatment, but not right now. But not right now. So that taking the test before they receive treatment because they're on the wait list can still give you a control, and they can still get the treatment later, and they are then you're getting like a pre-test of their own control. And then later when they're treated, you can compare their own scores to themselves in the past, which is very helpful when dealing with variability within a person, because it's the same person acting as their own control. You actually can deal with a lot of variance that way. Another control condition is obviously no treatment. Don't give them anything. Don't tell them they're getting anything. They're just not getting anything. But the last control condition here is best alternative. So even if you're not giving someone the depression medication that you're testing, you might give them something that's on the market, that's pretty common, that gets used all the time. And this gives you a baseline for your product to compete against, to see if you're doing really well against, right? It's not just something to beat a placebo, because a placebo is just a sugar pill. But if you can beat, what other competitors, that really shows the strength of your experimental design, and it shows the strength of your medication too. So between blinding and different control conditions, you can kind of fine tune your two-group design. And you can apply a lot of these blinding and control conditions to not just two-group design, but to other designs as well. Now that we've talked about some of the basics of two-group design, we can also get into the start of some statistical analysis. Don't worry, we're not getting into a statistical course. We're not doing any formulas or anything like that, just some basic things to know for any research design. So we're going to start with some basics to know about statistics. Statistics can be generally descriptive, or they can be inferential. They can describe a situation, or they can help you infer something about different groups, right? So in the bottom left here, you'll see that there's a bell curve. This is one way that we organize data. Bell curves are a really strong tool for describing pretty much any variable out there that can be measured in normal past nominal data, right? We're going to talk about that at length very soon, but first let's get into what does it mean for statistics to be descriptive and inferential. So descriptive means we're looking at different measures of central tendency or centeredness or averages, right? There's a couple of different ways of measuring averages, all because someone says your average, that doesn't actually let you know if it's mean, median, or mode, because those are three different ways to measure the middle, measure the average of lots of data, right? So a mean is where you sum up all of the answers, all of the scores from everybody, and then divide them equally, and that's the mean, right? Now the mean has pros and cons. It's typically it's mathematically very center. Now the problem with a mean though, it's very sensitive, very sensitive. All it takes is one person scoring way past the graph to change the mean and change the mean entirely to a place that doesn't really describe everybody else. What do I mean? So if I were to take the mean income of everyone in America, it would look very large. And the reason the mean would look very large is because there's a very few people way at the top end who make so much money that they pull the average really high up the graph, high up the scale. Now, most people, and like 80 to 90% of people, don't make the average amount of money anymore. They don't make the mean amount of money. So if the mean doesn't actually represent where most people are at, we would need to use a different kind of measurement, a median or a mode. Median is the centermost score on the whole scale, right? So if you have 10 scores, the median would be the score that's right in the middle between at number 5, or between 5 and 6, right there. 5.5 is the score there. It has nothing to do with how much that score is, like how much money that person actually made. It's just in the middle, right? So if we have 100 people in America that we're looking at, we're going to zoom in on person number 50 or 51 and say that's the median amount of income in America, because it's technically the middle of all the population. And that's one way to measure it, but sometimes that can also be a little skewed. And then mode is the score that happens most frequently. Score that happens most frequently. So one of the reasons you see income put into brackets, 0 to 20,000, 21,000 to 40,000, and so on and so forth, is because that lumps income together. And because it lumps income together, some brackets might happen more often than other brackets, right? So a chunk of America might show up in the 0 to 20,000 per year mark, but even more people in America show up in the 20 to 40,000 income bracket, right? And then fewer people end up in the 50 to 80,000 bracket. So mode is how often that score shows up. And the one that shows up the most would be the central measurement. So there's lots of different ways to measure the average or the middle, mean, median, and mode, and each one of them does something a little different. Another thing to know about descriptive stats is they show you how far something has to move from the middle to be considered different, right? And now let's go over to this bell curve. At this bell curve, you can see that there's a point in the middle, and that middle is average, right? That's where most of the scores line up, right? And that's why it's the highest point, because that's where most people fall. And then you can see this 34% and 34%. That is one deviation away from the middle, right? And then if you and you can see it starts to trail off, and the most people would fit, most scores fit in the middle. But then one more tail onto each side, you'll see 13% and 13%, right? That is 1 to 2 deviations away from the middle, right? So at that point, if you're 1 or 2 deviations away, between 1 and 2 deviations away, there's only 13% of people or scores who fall into that category, either higher or lower than the middle. So that distance kind of shows us how far away from average a score might be. And that's just describing the whole situation. That's just description, description, description. But when someone says the top 1% make most of America's money, what they mean to say is even further, you can see there's this 2.1% and 2.1% on each end of the bell curve. We're getting to the tails now. What we mean to say is that 1% is so far away from average, but they make most of the money in America, right? They are 2 to 3 standard deviations away from normal, and that's typically where we find the beginning of significance, statistical significance. And that's all just describing the situation we're in, right? But statistics can also be inferential, inferring conclusions, inferring differences, right? So let's look at this bell curve over here. And let's think of it as like height. Let's think of the numbers on the left as height, even though 0.1 and 0.2 and 0.3 are not height, but let's think of it as if it were height, right? Most people would be in the middle as average height. And then there are some people who are shorter and some people who are taller. They might be in the 13% group in that first deviation, that first standard deviation away from the middle. And then there are some people who are very tall and very short, and they are 2 standard deviations away from the middle. That's what that 2 with the symbol is, that's 2 standard deviations away. And -2 would be 2 standard deviations away from the middle, either smaller, shorter people or less money. We're getting away from the median or mean in the negative. So inferential stats is where we compare heights of one group, right? That's one bell curve, to the heights of another group with a different bell curve. And we take those two bell curves and we see if they line up or if they mismatch, or if they mismatch enough that they're actually significantly different. Significantly different. And there's lots of different tests to draw those conclusions. So another thing to know about stats is that bell curve is always assuming something. It's always assuming normal distribution. It's always assuming normal distribution. It's assuming that average is middle and 2 to 3 standard deviations above and 2 to 3 standard deviations below are significantly fewer scores, right? That bell curve shape is an assumption that data is normal. Now, your first question should be, well, what if data is not normal? This is going to sound like cheating, but with every graph, you can see that there's an X and Y axis, right? Statistically and mathematically, you can just change the axis measurement scales to create normalcy again, right? Now, if my scale at the bottom of my height graph goes from 0 inches to 2 inches tall, everyone's going to skew to one side, right? Everyone's going to skew to one kind of like off the edge of that graph, way past that measurement tool. So that's not a normal bell curve. That's not a normal distribution. It's not cheating, but it does sound like cheating, but it's not cheating to just change that scale at the bottom to better fit the data, right? So if everyone's obviously taller than 2 inches, what you do then is you change your scale at the bottom. You change it from 0 to 2 inches. You change it from 0 to 400 inches, right? And now suddenly people are a lot more distributed in the middle, far away from 0 and kind of far away from 400, to give you a distribution in the middle that looks more normal. It's not quite cheating. You're just changing your graph. You're changing your statistical assumptions to better fit the data to get that normal that's distributed, right? The only thing that sounds weird about this is that, well, if I can just change my scales up, then how does that let me know that things are actually like reflecting reality? Well, in reality, average means the thing that happens the most, right? And then what's not average is people scoring much higher than that or much lower than that. But average means the thing that happens the most. So statistically, that's all we're doing. We're just restructuring the graph to represent average as the thing that happens the most in the middle. And you just have to make sure your numbers do that too. So it sounds bad that you're reworking your stats to find normality, but that's a very common statistical function that we will do more talking about later. I hope you guys learned a lot about two-group design today. I hope if you have any questions, go ahead and send me a message, and I hope you have a good one. Bye.